So our Arduino Mega board is powered with your average desktop PSU. I pulled it out of some random computer that I found on the side of the street. It's just a 150 volt or something like that, or sorry, 150 watt, and it powers both the Arduino and the gauge cluster. Uh, it's 12 volts, so it's similar enough to a 14 volt car battery. So the gauge cluster is a little bit dimmer than it might be inside of a vehicle, but it gets constant power, and that's really all it needs. And then we use just a regular USB to connect the Arduino to the computer where it grabs data. And then there's a CAN bus shield that intermits between the Arduino and the gauge cluster. CAN bus is controller area network. It's inside gauge clusters, controllers, joysticks, just about any small PCB circuit board is controlled by some type of CAN shield, and that's what we're using here um, to send byte arrays to the gauge cluster. Here is our demo. It's just Assetto, the game, running with the cluster next to it. The tachometer, the speedometer, and the gear indicator are fully functional. You can see with the game on the right that, just a sec, that like right here, I'm in third gear, I'm in drive, obviously the car is moving. 112 kilometers, that's roughly 112, and there's no actual number, but the output from the game gives me an actual number that I can use to transmit to the gauge cluster itself. Now some challenges that we had along the way. The USB 3.0 connection is at peak 5 gigabits per second. That's how fast you can transmit data. And the Arduino can send and receive data that fast, but the CAN bus shield that we used, and CAN bus in general, is not nearly that fast. There's no need for 5 gigabits per second when you're sending one byte every few milliseconds. I mean, it's just not necessary. So gauge clusters aren't prepared to receive that much data that fast. So within the Arduino program, we have a buffer that delays the the Arduino still receives data every time the game sends it, but the data is delayed to the gauge cluster, so only every few pieces of data that it gets transmitted actually gets sent to the gauge cluster, and that way we get smooth readouts on the gauge cluster. It's not trying to jump back and forth between misinterpreted data. Like if you were at 5,000 RPMs and then for a split second you were at 3,000 because you shifted gears, and then you're back at 5,000 because you shift gears again, the gauge cluster would try and hop around back and forth between those RPMs, and we wouldn't want that. So we have a buffer in there that allows for smooth data. And then obviously finding out what bytes triggered which parts of the gauge cluster. So in the code there are different memory addresses within the microchip on the CAN bus processor on the gauge cluster. For example, the gear indicator itself is one address. It's 0x225, and that address controls, that register only controls the gear indicator, and you send a byte array to that address, and it reads that array, and it uses the data that you sent it to just change that. And so it goes, there are tons and tons of registers. I ran an oscilloscope with a loop in the background that calculated, it would record input, and then if something happened in the gauge cluster, it would output what address it was and what byte array it had just read, and then I used that in cahoots with an oscilloscope to see where in the addresses things were happening. So we nailed it down to 4 different addresses. The speedometer and the tachometer are on the same address. The gear indicator is its own address, and the fuel and temp gauges are their own address. But other than that, once we got past that hurdle, the rest of it was just coding, and it was rather easy actually after that.